Welcome back to my YouTube channel. Let us drill with this question, right? We've given here a solid shaft. I want guys to explain this. A solid shaft with a sleeve was still under strength of material N6, right? We're still under N6, right? So we have given here a solid shaft with a sleeve. I want us to understand this context, right? If you're given that, so if we read here, it says when a solid shaft is pressed into a sleeve, there will be an interference field, right, between the two parts. Okay, then says calculating the stresses in the sleeve is the same as we are using, is the same as for hollow cylinder. The formulas, they don't change, is what they are trying to say. If the shaft is hollow, then the problem is a compound cylinder. Okay, we'll discuss about this. I will make a video about compound cylinder. Actually, after it will be a next video after this one. If you have subscribed there, you will be alerted, and then if you have clicked that notification button, you will be alerted, right? So we'll deal about this. For now, let us forget a bit about this. But when the shaft is solid, I want us to focus on this. When the shaft is solid, says the internal radius of the shaft tends to 0. Okay, which is fine. No problem about that. We'll discuss about this. What is important thing you must know now, the force, as we know, the force is equals to pressure multiplied by area. Pressure we have given here is pressure. The area is pi dl. That is how we calculate the pressure. This is the formula for force required to push the sleeve. The formula required to, you see, this is a force, but now here the formula for the force required to push the sleeve onto a shaft. Force required to push the sleeve onto the shaft. Let's say we are given a sleeve like that. Make an example. Then we have a shaft. This shaft, it will be a force. They're trying that the force that will push. Okay, initially we'll discuss about this. There's a sketch about that. There's a sketch. The force required to push the sleeve into the shaft is this one. Take note. Coefficient of friction. Pressure, remember, is the same as radial. Pressure that is internal is the same as what? Radial stress. Right. That is the internal pressure. Multiplied by pi. Diameter of a what? Common diameter. This is a common diameter. Then the length of the sleeve. So if you can check here, the force feet is in Newton. Coefficient of friction has no SI unit, pressure in Pascal. Common diameter. This is a common diameter. We'll be using common diameter, which is what it is measured in meter, the length of the sleeve. So the torque transmitted, we know, is force multiplied by radius, force feet. So the force feet is this one. This is a force feet. As you can see, all of that would be equals to force feet multiplied by radius, which is common diameter again, multiply common diameter divided by 2. You know, this is same as radius, like that. So this would have the torque there. You know, the torque is force multiplied by radius. So if given the torque, we know this. So what I'm trying to say here is the structure. The pressure exerted all over the contact surface. If you check, guys, here, this is a sleeve. Here we have the sleeve. Here it's a sleeve. Here section, we have our sleeve there. can say this sleeve is the same stick cylinder there, but here we have what again? This is a shaft. The force that will require to enforce the shaft to enter guys to this sleeve, that force will be calculated by this formula. That's what I'm trying to say. It will be calculated by this formula, the one that we have here. That will be the formula, right? That is the force. If you're given this is a shaft in the sleeve, it's a sleeve, remember dealing with the sleeve. And remember, first we are dealing only with the cylinder. Now it's a sleeve and the shaft, in the solid shaft, or you can say solid shaft and the sleeve or cylinder. Big cylinder and the solid shaft is what we are trying to say here. Now we are trying to put, remember, it's like that. Now as we have sectioning, that means indicating that we have put, now is no longer a hole, we have there it's a shaft that we have put it in, we have applied the force, we have tried to squeeze the shaft like that. Hopefully you'll understand this, guys. So that is what we'll have there. Then as you can see, the length of the sleeve, the diameter is the one inside diameter, coefficient of friction, right? Then as you can see, if you manipulate here, if you manipulate, but d is equal to 0, common diameter. As you manipulate, they manipulated by us, at the result they got that b is equals to 0. As you can see here, they say radial stress is equals to a, also the hook stress is equals to a. What do you notice here? You see we have a. In other words, it's meaning that the hook stress is equal to radial stress is equal to hook stress. Okay, let us discuss. They've shown us here, and they say formula for pressure at the contact diameter. What is the contact diameter? The contact diameter is this one, guys. Here it's a contact diameter. Here it's a contact diameter. It's there. It's in contact. Remember now, the sleeves, it's in contact. That is a contact diameter. That will be a contact diameter. That is our contact diameter there. So as you can see, at the pressure at the contact diameter by the contact diameter is also the inside diameter. The hook stress, if you have given a sleeve and a solid shaft, you must know that the hook stress, guys, the hook stress is equal to radial stress. Whereby we know that radial stress is the same as what is pressure. Take note of that. Only when you are given a sleeve, you have given a sleeve with a shaft, guys. Only when you are given a sleeve with a shaft at this common diameter, we must know that the hook stress only at the common diameter, must understand that only at the common diameter. Here at the common diameter, we must try to understand that here at the common diameter, which is the same as the inside diameter, but it's a common diameter. We must know this at the common diameter there. You can say DC, which is common diameter, represent the C. The hook stress is there. It's equal to radial stress. Whereby we know that radial stress at the internal diameter is the same as what is pressure. Again, this is internal what pressure. Take note there, guys. Please take note there. Take note. And so this is simply what we have there. If you're given a shaft and the sleeve, shaft, guys, only when you're given a shaft and the sleeve, right? So yeah, we know this. Then example 1.7 show how to calculate the intermediate pressure at the contact diameter for a solid shaft with sleeve. Intermediate, you see, intermediate is this, guys. It's an intermediate here. Intermediate, we were talking about the internal pressure, the intermediate one, which is this one that we're talking about. is the same as radial. So here we have given what, if you may check, the hub of the coupling has to be strung onto a hollow shaft. As you can see, the hub that has to strung with the solid shaft. There is a solid shaft. It's supposed to be strung here. Remember, this is a it's how it's supposed. We want to apply the force to strung. To strung meaning to put inside by force. There we strung to put them together onto a hollow shaft. Here is a hollow shaft. It will take place there. That the power, if given the power is 30 kilowatts, can be transmitted. We've given the number of rev. Then the outside diameter is 50. The inside diameter is 30. The outside diameter of the hub is 80. The length is that. The coefficient of friction are given is 0.25. E is that. But here it says you should calculate. It says calculate the intermediate pressure at the contact diameter DC. This one, guys, I won't do it for you. I will just simply show you the example, because it's a simple. You have given power, guys. You've given power. If you are given power, you know that power is 2 pi nt over 60. Power. If you have power, then you will find torque. Power. Given power. So this I will show you, guys. What I want to do for you is not this one. Here it's our thing here. Calculate the intermediate pressure. The intermediate pressure, even this is not complete. This is not the intermediate pressure. It's not the intermediate. It's simply a torque. We've calculated the torque, but we know that the torque, guys, the torque, you must know the formula. What is the torque? Remember, guys, what is actually the torque? We've given the torque. Even here in the example, they are not finished. We know that the torque is force multiplied by radius. But we know this force, guys. The force is what is coefficient of friction multiplied by pressure multiplied by pi multiplied by common diameter. But the radius will be multiplied. Okay, here I'm also multiplied by length of the sleeve. Only this, guys, only that. It is what? It is the torque. But now we're supposed to multiply by the radius. How can we get the radius? We say diameter, the common diameter will divide by 2. This is the same as what is radius now. So what do we want? It is pressure. We want that pressure, guys. That is the aim, to calculate the pressure. Then you'll make the pressure the subject of the formula. You divide by all of this, guys. By all of that. Right? You'll divide by all of that. If you divide, if you know your maths, here you're going to have 2 torque divide by coefficient of friction multiplied by pi divided by common diameter, divide also by this, the another one, common diameter again. So you simply substitute your torque that you got here, you've calculated for us. Then coefficient of friction you are given here, pi, common diameter we have given. Then you'll find your pressure. So this one I will leave it for you guys. Here, the one that I will do for you now, you see that is so simple. The one that I will need to do for you guys, this example 1.8, so that we explain. Read here. It says a sleeve. Take a note. We are dealing with the sleeve with an outside diameter. We have given the outside diameter, and the inside diameter of that should be width of 120 millimeter. Is too long. Is 2 millimeter long. The sleeve is 2 millimeter long. A solid shaft note. That means note here again. A solid shaft of that 120 in diameter is to be pressed into the sleeve, resulting in the interference force of this of 30 megapascal. The coefficient of friction between the two shafts is 0.4. Calculate now the maximum and the minimum hoop stresses in the sleeve. All right, guys. All right. This is the type of form of nature that you have, guys. Let me do here. It's our sleeves. As you here it's our sleeves, guys. Maybe if I demonstrate this here, this is the shaft that we want to apply here. It's our shaft. Here is the shaft there. We want to press this shaft by force. We are pressing this shaft by force. Apply the force. You want it to fit there. We have that force that we apply. Whereby we know that force is what is calculated by pi multiplied by pressure multiplied by coefficient of friction. So this is the coefficient of friction multiplied by force multiplied by pi multiplied by common diameter multiplied by the length of the sleeve. Right, this is what we know. Then our common diameter is this one here. Between the diameter is common, is between the shaft and this, the shaft and the sleeve. We have now the common diameter there. I've highlighted it with red. That is our common diameter. Do not forget that the common diameter, what we have learned is that the hoop stress is equal to radial stress. Right, also this is the same as what is pressure, but we know these two are equal. Everything there, all of them, they are equal. Like this is the internal pressure or interference. You can say interference pressure, but it's the same. So this is what we have. Usually this is what we have. Okay, down they say calculate the maximum and the minimum of stress in the sleeve above, not in the shaft, in the sleeve. In the sleeve, guys, in the sleeve, I'm sectioning that sleeve. In that sleeve, I'm henching it there. That sleeve. So that is a sleeve, guys. We're still applying thick cylinder. This is the sleeve. Yeah, right. The sleeve will be like that. You understand? Without, now here we have a solid shaft. So we're focusing on the sleeve again. So how can we calculate this, guys? How can we come about finding the aim is to calculate the maximum? So guys, we come again now. You know, now you do your thing, guys. Yeah, remember not make a mistake. For sleeve, even for sleeve and thick cylinders, we are doing this structure. They said we are using the same principle. Yeah, we're still applying the same principle. Let me just do like this. Okay, it's fine. We're still under the same principle. Still use our stress distribution graph. We have given internal diameter, which is a common diameter, but here we'll have common. I won't say inter, I will simply say common diameter. We have a common diameter now. Instead of internal will be common. It now becomes common. Then here we'll have what? The outer diameter. The outer diameter. Outer. Understand? This is not, now we have common like that. The common diameter we have given that, okay, the outside is 150, the common diameter is 120. So we've given these diameters. Common diameter here, 120 is the same as 0.12 meter. That is 150, 0.15 meter. Right. So a shaft is that, okay, it's the length of the shaft long here, which is same as 0.12. is the distance there. So also it has the diameter. The shaft also has a diameter of 120. Well, the shaft here is that diameter. The shaft by its own has the diameter of 0.12 meter. Then we have coefficient of friction is 0.4. Coefficient of friction there, which is 0.4. Then what we have, this says now, is pressed into the sleeve, resulting with the interference pressure of 30 megapascal. Oh, good, this is fine. Oh, good. Nice one. Interference. Now we know that the interference is equal to this. It's the same as you call the radial, guys. The radial internal pressure, the process does not change. Internal pressure is like this. Isn't it? Or let me just not write it like that here. For you to understand, let me just do like this a bit. Can you see radial like this is equal to, again, internal interference pressure. So right on the internal, on the common diameter, remember the interference or internal pressure that will take place, interference pressure is taking at the common diameter. All right. So we're applying our things now. Right. Remember, how can you view this? If you are looking at this side, you will see a shape like this, cylinder like that. Then there we have our common diameter. Basically here we'll see the solid shaft, whereby I can do like this. Also here we'll have some solid shaft. Let me just section like that. You see that will be, you'll see also something, the solid shaft here. All right, but however, never the small, this is still a stick cylinder, guys. This sleeve, you see, we still have something like a cylinder, so we can apply the thick cylinder method there. So we know that we still apply the method. We know from here going that size, we still gonna apply the internal pressure stress distribution graph, but now goes with the shaft like this. Then we come like that. So yeah, this is minus this. We know this is for radial, it's for hoop stress. So yeah, now radial can say, let's start now. I can tell the examiner that we're working. I can say I'm working at the common diameter, because now if we have a sleeve, we're dealing with common diameter, guys. Common diameter, you can say DC, by that is 0.112 meter. We're working here so that they will understand. So hence you have told, so now the examiner knows the radial stress. We know there at the common diameter. We come to our graph, we check, do we have, he said is the same as interference. From here we have the interference pressure, I've given it, which is 30. You see, then now when you write it here, must be negative because it's on the negative region. Here we have 0, you have 0, because this region is negative, will be negative 30 megapascal at this point, right at our common diameter. So we know that is simply equals to minus 30 megapascal, right, at this diameter, at the common diameter. We have that, but we know that the radial is given by a minus b over d squared. Right, this is a common diameter. So our radial we know is negative 30 times 10 to the power of positive 6. Then a we don't know, b we don't know, common diameter we know is 0.12. Then we square this, guys. As we square this is simply, there's nothing we can do, we'll call it equation 1. What else do we know? We don't know about the maximum hook stress there. We don't know about that hook stress, the maximum one. We don't know about this minimum hook stress here. But we do know about the radial stress there, the minimum radial stress. We do know because it's here, it's at the 0. You see this line is lying, is touching at the 0. It's here at the 0. So there is 0 megapascal. So we know that radial is equals to 0 there. So we can come again. We know that we have this equation, radial a minus b over d squared. Here will be 0. But do not just go there. We are working at what now? At diameter. At this diameter. So tell the examiner at again diameter. Show it at diameter. You can just write like this. What is the diameter? 0.5. 0.5 meter. We are working at this so that our thing will be smart. There, the radial we have it is 0 megapascal FCFC. But what is this? We know is given by this formula, a minus b over d squared. So here we have our 0. A we don't know, b we don't know, d we know is 0.15, but don't forget to square. So we can make a the subject to take it the side, or you can take a, yeah. If you make a, remember a will be simply b, will be b over 0.15 squared. That is our a. Now since you've done this, use substitution. You can say you can call this equation 2, substitute 2 into 1 into equation 1. Where is equation 1? Here it is, guys. So we substitute. If we see a, where we see a, we'll replace this a with this whole thing there. As you can see, that is equals to a. So we'll have minus 30 times 10 power 6 is equals to a there, simply b minus in over 0.15 squared minus b into 0.12 squared. As you can see, if this mathematics you find it difficult for you, if you find it difficult, this is the same as we have 1 like that, the same as 1 over 0.15 squared. You punch this, you have b. So it's up to you which method to use. It's the one and the same thing, guys. So all right, here I have minus 30 times 10 power 6 is equals to that. This is maths now. This one, it might trouble you because I know you're forgetting your fraction, the laws of fractions, because now just just punch your calculator like that. Here we have 1 and punch it like that to make your life safe and easy, right? To make your life just nice and marvelous and simple, just like that. All right, isn't it? So if you make your life like that, so easily like that, let us make our life. Let me just show you what I'm meaning. If you take your calculator, we say 1 over 0.15, then you square. You'll simply have this. If you punch like this on your calculator, you'll have 44,444, but you have a p there. 44p minus. Here is same as 1 of like that. To punch that, you'll have 1 over 0.12 squared. Then you'll have 69,444b. Make your life easier, make your life simple, but this obvious is b and p. This is just a like term, so you subtract now. 44.444 minus 69,444, right? You will have this to be here. This side we still have minus 30 times 10 to the power of 6. Here we'll simply have minus 25 p. Then divided by minus 25 there, by negative 25 is here dividing what I'm doing. So this and this will cancel, this and this will cancel. Therefore p, if you punch that, our p will be 30 times 10 to the power of 6. Then we divide that by 25. Oh, solid number here. This is same as 1.2 times 10 to the power of what? 6. This is b. Then you can substitute this into a here. We have a. Yeah. Can find a again. When we see p will be 1.2 times 10 to the power of 6 into 0.15 squared. A, therefore a. What will be the value of a? If you can say 1.2 times 10 to the power of 6 divided by 0.15 squared. This will be 53,333 times 10 to the power of 6. Remember, this thing a and b has no SI units. So we have this. Multiple. The question says we should calculate the maximum. Here it's a maximum. The maximum and the minimum hook stresses. The maximum and the minimum hook stresses in the sleeve. So it's simple. We know how do we calculate the hook stress is given by this formula: A plus B over D squared. Do not make any mistake, it must be plus here. If you put negative, you'll be doomed. So can say, come here, H maximum. They say max, we know will be at the max will be at the common diameter. A, we have now A is that is 53.333 times 10 to the power of 6 plus B. What is B? Is 1.25 times 10, 1.2 times 10 power of 6. Divide now by a common diameter, which is 0.12 squared. From here, guys, see the maximum lies in this diameter. There. It lies in this diameter, that maximum point there. So There we punch our calculate, you'll get this 136.667 obvious megapascal. Then H mean, we want the mean, this will be at the outer diameter. We know our formula also would be at this diameter, outer diameter, or by outer diameter 0.15. So our value of A is 53.333 plus B, which is 1.2 times 10 to the power 6. The diameter now would be 0.15. We square, then the minimum hook stress will simply equals to what? It will be 106.667 megapascal. Right. Remember, hook stress is tensile. If you want, you can show, but there's no need. But just for in case, hook stress is tensile. Tensile, it's a hook stress, guys. If you hear the word tensile, it's a hook stress. We are done with this. No. Question 2, guys, says they calculate the force required to press the shaft on the sleeve. Now the force required, I've talked about that force, is said is this one. Here's the formula. That is torque, okay? The force required to push the sleeve into the shaft is this one. There, you see, F is equals to coefficient of friction multiplied by pressure, which is interference, multiplied by pi, multiplied by common diameter, multiplied by the length. This is the length of the sleeve, you see. So I've talked about this, guys. Yeah, I understand. It's better if I did just then we have this now. They missed the force coefficient of friction, it was 0.4. I remember here it is. Coefficient of friction is 0.4. Pressure is 30 megapascal. As you can see the pressure there. Yeah, common diameter, it was 120. The length, and then the length of the sleeve is 20 millimeter long. So yeah, guys, that is what we have. So nevertheless, pressure, it is 30 megapascal times 10 to the power 6 multiplied by pi, common diameter, it is 0.12, which is multiplied by length, it was 200, divided by that, it's the same as 0.2 multiplied by, yeah, it's enough like this. So we crunch this, guys. Insert this on our mistake calculator then. I don't know what did you got there. Tell me. So you approximately gonna get this to be the force 904,779. This is in kilonewton. You can leave it in newtons if you want. So number 3 says we should calculate what? The torque that can be transmitted without sleep. Okay. How cool is this? the torque will be equal to force multiplied by the radius, but common radius. The force already have calculated it is 9, like that, 779 multiplied by common radius. Common radius is the same as common diameter divided by 2. Yeah, like if you divide, this is 0,1, 2 divided by 2 is the same as 0,06 multiplied by 0,06. Then this will be 54,287 obvious kilonewton, but this is per what meter. So this is what it is, guys. So thank you for watching, guys. Please do not forget to subscribe to my YouTube channel and click the notification button so that you'll be notified whenever I post a new video. Stay tuned and stay notified. Remember, the next session will be dealing with compounds. The one, the thick cylinder, the compound one. So all the best, guys.